The universe is held together by a ghost. Galaxies spin within vast invisible halos, and the cosmic web is woven from threads we cannot see. The astronomer Vera Rubin put it perfectly when she said the discrepancy between what we see and what must be there is enough to make your head spin. Over a quarter of everything that exists is made of a substance that refuses to show itself, a cosmic placeholder we call dark matter. By the end of this journey, you will understand not just why this mystery defines modern physics, but how close we might be to cracking it open. What is this shadow material that sculpts the cosmos, and why has it evaded every trap we set for it? We will trace the hunt from a shocking observation at a telescope to experiments miles underground and theories that stretch the fabric of reality itself. The answer, when it comes, will rewrite our story of the universe. What do you think it feels like to chase something you cannot see? Her telescope pointed toward the great spiral of Andromeda, our closest galactic neighbor. It was the 1970s, and astronomer Vera Rubin was not looking for a revolution. She was simply trying to measure how fast stars orbit the center of a galaxy. According to the laws of gravity as we understood them, it should have been a simple story. Stars near the center, with all that visible mass pulling on them, should zip around quickly. Stars out at the lonely edges far from the bright core should slow down just as planets farther from the Sun move more slowly in their orbits. This was the prediction, a clean curve that should have dropped off into the darkness. But the data from her spectrograph told a different tale entirely. The stars at the very edge of Andromeda were not slowing down. They were whipping around just as fast as the stars near the center. The rotation curve was not dropping. It was flat, a stubborn, unwavering line that defied every expectation. Vera Rubin later called the result astonishing. It was not a small error or a measurement glitch. It was a fundamental disconnect between what we saw and what was holding the galaxy together. The visible stars and gas simply did not have enough gravitational pull to keep those outer stars from flying off into intergalactic space. Something else was there, providing an immense, invisible anchor. The only explanation was a vast halo of unseen mass enveloping the galaxy, a halo that outweighed all the glowing stars and nebulae by a factor of 10 to 1. Think of it like this: if you watched a merry-go-round, you expect the horses on the outside edge to feel a stronger tug, to need more force to stay on. Now imagine if the horses on the very outside were moving just as fast as the ones near the center, with no visible mechanism pulling them. You would be forced to conclude there is an invisible structure, a hidden framework holding the entire ride together. That is what Rubin's flat rotation curves revealed. The immediate reaction in the scientific community was a mixture of deep skepticism and intense curiosity. Here was robust, repeatable evidence that could not be ignored. It built upon earlier hints from other astronomers, but Rubin's work was so clear, so meticulous, that it turned a curious anomaly into a central problem in physics. How would you react if your most careful work revealed a universe that did not obey the rules you had trusted? This was the historical spark, the moment the cosmic detective story truly began. The hunt was no longer for a theoretical possibility. It was for a tangible, overwhelming presence that was sculpting the cosmos right before our eyes, yet remained utterly hidden from them. The universe is a funhouse mirror on the grandest scale. Look deep enough into space and you will see galaxies stretched into arcs, smeared into wisps, or even repeated like a cosmic echo. This is not a flaw in the telescope. It is a fundamental prediction of Einstein's theory of gravity, a phenomenon called gravitational lensing. Wherever there is mass, it warps the fabric of space-time around it. Light traveling from a distant galaxy must follow this curved path, bending around the massive object in the foreground. The result is a natural magnifying glass and a distortion that reveals the invisible. As physicist Kip Thorne once described it, it is one of the most elegant demonstrations of how mass tells space how to curve, and space tells light how to move. For dark matter hunters, this is a gift. We cannot see the dark matter itself, but we can see its gravitational handiwork, the way it bends the light from objects far behind it. This allows us to literally map its distribution across the sky. There are two primary ways we see this effect, one dramatic and one subtle. Strong gravitational lensing creates those breathtaking Einstein rings and multiple images, where a foreground galaxy cluster acts as a nearly perfect lens, warping a single background galaxy into a perfect circle of light. It is a direct, unmistakable signature of immense mass, but more common, and in many ways more powerful, is weak lensing. Here, the distortion is far more gentle. Instead of creating perfect rings, a vast cloud of dark matter will subtly shear and stretch the shapes of thousands of background galaxies, like looking through a warped windowpane. By statistically analyzing the slight, coherent alignment of these stretched galaxies, astronomers can create a detailed mass map of the intervening dark matter, tracing out the invisible cosmic scaffolding. The most striking proof of this tool came from observations of a system known as the Bullet Cluster. This is not a single galaxy, but the aftermath of a violent collision between two enormous galaxy clusters. When these titans smashed together, the clouds of hot, visible gas, the normal matter, slammed into each other, heated up and slowed down, lagging behind in the center of the crash. But the dark matter halos of the two clusters, according to the weak lensing maps, did something astonishing. They passed right through each other and kept going, now separated from the visible gas. This was a visual revelation. What does it mean that dark matter could sail through such a cataclysm unscathed, while normal matter got stuck in the middle? It tells us that dark matter does not interact with itself or with light in any significant way. It feels gravity and almost nothing else. It is a ghost that can walk through walls, a substance so aloof that even in the most violent cosmic events, it simply goes its own way. This observation moved dark matter from a theoretical necessity to an observed, mappable component of the universe. We could now see its shadow cast upon the light of distant galaxies. But how do we weigh a ghost? To find the total amount of dark matter in the entire cosmos, we needed to listen to its oldest echo. Imagine scientists as cosmic archaeologists, tuning their instruments not to the light of stars, but to a faint, cold whisper that fills every corner of the sky. This is the cosmic microwave background, the afterglow of the Big Bang itself, released when the universe was a mere 380,000 years old. It is the universe's baby picture, and etched into its subtle glow are the seeds of everything to come. Two space missions, the Wilkinson Microwave Anisotropy Probe, or WMAP, and later the European Space Agency's Planck satellite, spent years mapping this faint radiation with exquisite precision. They were not looking for images, but for tiny temperature differences, minute wrinkles in the fabric of space that were mere millionths of a degree. As one project scientist described it, they were reading the universe's own birth certificate. The pattern of these fluctuations is not random. It tells a precise story of pressure and gravity in that primordial soup. Sound waves called baryon acoustic oscillations rippled through the hot plasma of the early universe and then froze in place when atoms formed and light was set free. The scale of these frozen ripples, visible as a series of peaks in the cosmic data, acts as a standard ruler. By measuring this ruler, scientists could calculate the exact composition of the universe with unprecedented accuracy. The recipe they deciphered is both humbling and definitive. All the stars, planets, galaxies, and gas we see, every atom of normal matter accounts for only about 5% of the cosmos. Dark matter, the invisible gravitational scaffolding, makes up roughly 27%. the remaining 68% is something even more mysterious, a force driving the universe's expansion that we call dark energy. This cosmological framework is our most vital clue. It tells us not just that dark matter exists, but exactly how much of it there is. The positions of those acoustic peaks constrain the total density of matter in the universe, ruling out whole classes of potential explanations. Any successful candidate for dark matter must be abundant enough to account for that 27%, and it must have been present and influential in those first moments, shaping the wrinkles we see today. So the question is not just what is out there, but what particle or substance fits perfectly into this cosmic recipe, a recipe written in the faint chill of the Big Bang's fading light. Particle physicists found themselves in a unique position, reading the story of the cosmos written in the sky, and then turning to their own machines to search for the author. If dark matter sculpts galaxies and fills the universe, it must be made of something. The most compelling answer for decades came not from astronomy, but from a beautiful symmetry in particle physics known as supersymmetry. This theory proposes that every known particle has a heavier, shadowy partner, and the lightest of these hypothetical partners, stable and neutral, would be the perfect candidate for dark matter. It was dubbed the WIMP for weakly interacting massive particle. The appeal was immediate and profound. As one theorist famously noted, it felt like a miracle. The calculations showed that if these particles existed in the early universe, they would have annihilated with each other until their numbers thinned out, leaving behind just the right amount of dark matter we observe today. The predicted relic density from these elegant equations matched the 27% measured by the Planck satellite with astonishing precision. It was as if the universe had left a fingerprint that perfectly matched a glove particle physicists had already been designing. So what exactly is a WIMP? Imagine a particle with substantial mass, perhaps hundreds of times heavier than a proton, but one that is profoundly aloof. It would feel the pull of gravity, binding it into the vast halos around galaxies. And crucially, it would also interact via the weak nuclear force, the same force behind certain types of radioactive decay. This is an incredibly feeble interaction, far weaker than the electromagnetic force that makes light bounce off normal matter. This dual nature explains everything. The weak force interaction in the early universe governed how WIMP paired off and vanished, setting their final abundance. Their weakness today is why they are dark. A WIMP could pass through the entire Earth, through you, as if we were not even there, only very rarely bumping into the nucleus of an atom. This ghostly behavior is both the challenge and the clue for detection. Scientists devised two main strategies to catch one. Direct detection experiments wait deep underground, in mines or beneath mountains, shielded from cosmic rays. They use ultra-pure crystals or vats of liquid xenon, chilled to extreme temperatures, hoping to sense the minuscule vibration or flash of light from a single, rare collision between a passing WIMP and an atomic nucleus. It is like listening for the faintest possible tap on a single bell in a vast, silent cathedral. Indirect detection looks for the aftermath of WIMP annihilating each other. If two WIMP collide in the dense heart of a galaxy or the Sun, they could transform into a shower of familiar particles we can see, like gamma rays or neutrinos. Telescopes scan the skies for these unusual signals coming from places dark matter is thought to congregate. For years, this elegant idea guided the hunt. But it prompts a deeper, almost philosophical question. Is the universe obligated to be elegant? Does the beautiful fit between a particle theory and a cosmic measurement mean it must be true, or have we been seduced by a mathematical mirage? To answer that, we must descend into the quietest places on Earth. Deep beneath the rolling hills of South Dakota, the world goes quiet. The Homestake Mine descends over a mile into the Earth, a place where the constant rain of cosmic rays from space is reduced to a faint whisper. Here, in the Sanford Underground Research Facility, scientists have built some of the quietest rooms in the universe. Their goal is not to hear silence, but to break it with a single, unimaginably rare sound, the ping of a dark matter particle finally saying hello. This is the frontier of direct detection, a patient, decades-long vigil for a ghost to brush against the material world. As one researcher described the environment, it is about creating a cathedral of stillness where even the faintest signal can be heard. The principle is deceptively simple. If dark matter particles like the theorized WIMP are streaming through Earth, then a few should occasionally bump into the nucleus of an atom in a detector. That collision would transfer a minuscule amount of energy, causing the atom to recoil. The challenge is that this recoil is incredibly tiny, like sensing the vibration from a single grain of sand dropped a mile away. To even have a chance, every other source of vibration and energy must be eliminated. The greatest enemy is not the darkness of the particle, but the light of our own world. Natural radioactivity is everywhere, in the very rocks of the Earth, in the materials used to build the detectors, even within our own bodies. Eliminating this background noise is an epic feat of engineering and purity. Detector components are forged from ancient, low radioactivity metals, like lead salvaged from sunken Roman ships, whose radioactivity has decayed over millennia. The experiments themselves are bathed in ultra-pure water or shielded by tons of purified material, all to block out the persistent hum of the natural world. Within these shielded caverns, two main technological approaches have led the search. The first uses cryogenic crystals like germanium or silicon, cooled to a fraction of a degree above absolute zero. Experiments like Super-CDMS, the cryogenic dark matter search, operate at these temperatures where a single particle collision produces both a tiny vibration and a slight increase in heat. By measuring these two signals together, they can powerfully distinguish a potential dark matter event from background noise. The second, and currently most sensitive, approach uses liquid xenon. Enormous vats like those in the LUX-ZEPLIN or XENONNT experiments hold tons of this noble liquid in a state of ultra-purity. When a particle interacts in the xenon, it produces a flash of light and knocks electrons loose. Sophisticated sensors map the precise location and nature of these signals in 3 dimensions, creating a detailed picture of each event to weed out imposters. The sensitivity of these instruments is almost beyond comprehension. They can rule out entire ranges of possible dark matter particle masses and interaction strengths, carving away vast territories on the map of what dark matter is not. Yet, after years of collecting data, the story these detectors tell is one of profound silence. The expected ping has not arrived. Every blip, every candidate event, has upon ruthless scrutiny been traced back to a neutrino from the sun or a trace radioactive decay. This leads to a pivotal and haunting question. What does a null result actually mean? In science, the absence of evidence is not evidence of absence, but it is a powerful guide. The persistent quiet from these exquisitely sensitive laboratories tells us that if dark matter is a WIMP, it interacts even more weakly than our most optimistic models predicted. It is shyer, more elusive. Each experiment that comes up empty pushes the possible hiding places for this particle into more extreme, more finely tuned corners of theory. The silence is not a failure, it is a data point, a whisper that is forcing us to listen more carefully and to look elsewhere. With the underground labs listening intently, the search naturally turns upward to the skies where dark matter's ghostly presence might betray itself in a different way. A ghost may be silent, but it can still leave footprints. While underground labs listen for a direct whisper, other scientists scan the heavens for the faint, secondary glow of dark matter's shadowy activities. This is the art of indirect detection, the search for the cosmic aftermath. If dark matter particles are their own antimatter, as many theories suggest, then when two of them collide in the dense heart of a galaxy or a star, they could annihilate in a flash, transforming into a shower of particles we can see, gamma rays, neutrinos, or antimatter like positrons. It is a hunt for the ghost's discarded fingerprints. As one astrophysicist working with the Fermi Gamma Ray Space Telescope put it, we are looking for a faint, anomalous light in places where darkness is deepest. The most promising hunting ground is the very center of our own Milky Way. According to our best maps, this region should be packed with dark matter, a dense knot in the invisible web. Telescopes like Fermi's Large Area Telescope have spent over a decade staring at this region, cataloging every gamma-ray photon, the highest energy form of light. The data revealed something intriguing, a faint but persistent excess of gamma rays at a specific energy emanating from the galactic center. For a time, this galactic center GVXS sparked real excitement. Could this be the long-sought signal of dark matter particles annihilating? The challenge, and it is a monumental one, is that the universe is a noisy place. That same region is also filled with pulsars, the rapidly spinning corpses of dead stars, and clouds of cosmic rays slamming into gas. These astrophysical processes also produce gamma rays. Distinguishing a dark matter signal from this cacophony is like trying to hear a single, specific instrument in a symphony when you are not entirely sure of the tune. The debate over the GVXS continues, a perfect illustration of the meticulous detective work required. Every unusual bump in the data must be interrogated. Is it a statistical fluke? Is it a previously unknown type of pulsar? The search employs different messengers to cross-check any potential signal. Deep in the ice at the South Pole, the IceCube Neutrino Observatory uses a cubic kilometer of Antarctic ice as a detector. It watches for the faint blue flashes of light created when a neutrino, another ghostly particle, interacts with the ice. A sudden concentration of high-energy neutrinos from the Sun, where dark matter could accumulate and annihilate, would be a spectacular clue. Meanwhile, instruments on the International Space Station, like the Alpha Magnetic Spectrometer, meticulously count cosmic ray particles, searching for an unexpected surplus of antimatter positrons that could point to dark matter decays in our galactic neighborhood. Each of these messengers, gamma rays, neutrinos, antimatter, tells a different part of the story, and a true discovery would require a consistent signal across multiple channels. So we return to that pivotal question: how do we know if a bump in the data is a discovery or just cosmic noise? The answer lies in patience and prediction. A real dark matter signal would have a specific energy signature predicted by theory, and it would align perfectly with the predicted distribution of dark matter in space, concentrated in halos and not necessarily where visible matter glows brightest. The celestial search is a perfect complement to the quiet vigil underground. One listens for the ghost's touch, the other looks for its faded shadow on the wall. Yet, as both methods return intriguing hints but no definitive proof, a profound realization settles in. Perhaps the ghost is not just shy. Perhaps we have been searching for the wrong kind of ghost entirely. The persistent silence from the underground laboratories is not a dead end, but a signpost pointing in a new direction. What if we have been imagining the ghost all wrong? For decades, the hunt focused on heavy, sluggish particles, the WIMP. But what if dark matter is not a bullet, but a breeze? What if it is not a single, massive entity you could, in theory, weigh in your hand, but something so lightweight it behaves more like a wave, a field that fills the cosmos like a silent hum? This is the promise of the Axion, a hypothetical particle born not from cosmology, but from a deep and elegant puzzle in the heart of nuclear physics. The story begins with a question so precise most of us never consider it. Why is the neutron so perfectly symmetrical? Inside every atomic nucleus, particles called neutrons are held together by the strong nuclear force described by a theory called quantum chromodynamics. This theory allows for a certain kind of asymmetry, a parameter that should make the neutron ever so slightly electric, giving it what is called an electric dipole moment. Physicists have measured this property with incredible care, and the result is zero. The neutron is perfectly round to an astonishing degree of precision. This presents a fine-tuning problem known as the strong CP problem. Why does nature choose this one perfectly symmetric value out of infinite possibilities? In the late 1970s, theorists Roberto Pexi and Helen Quinn proposed a beautiful solution. They suggested a new, fundamental symmetry in the laws of physics that would naturally force this asymmetry to zero. Shortly after, physicists Frank Wilczek and Steven Weinberg realized this mechanism would produce a new, very light particle. Wilczek named it the Axion after a brand of laundry detergent because he thought it could clean up the problem. The Axion was born to solve one mystery, but it soon became a prime candidate for another. If these particles exist in vast numbers, they could collectively make up the cold, dark matter that shapes the universe. But here is the profound shift. An axion would be billions of times lighter than an electron. You would need a staggering number of them to account for the missing mass, a number so large it is difficult to comprehend. They would not exist as discrete, bullet-like particles streaming through space. Instead, they would form a coherent, oscillating field that permeates every corner of the cosmos. Think of it not as a rain of invisible marbles, but as an ocean of invisible waves, a quantum hum filling the void. This wave-like nature changes how we search for them. The most promising method exploits a predicted interaction between axions and electromagnetism. In the presence of a strong magnetic field, an axion should have a tiny chance to convert into a very low-energy photon, a microwave radio wave. The hunt then becomes an exercise in extreme listening. The leading experiment is called ADMX, the Axion Dark Matter experiment. It operates at the University of Washington inside a powerful superconducting magnet. At the heart of the device is a resonant cavity, a metal chamber designed to amplify a specific microwave frequency, like the body of a guitar amplifying a single note. The idea is to tune this cavity across a wide range of possible frequencies, corresponding to different possible axion masses, and listen intently for an unexpected whisper of microwave photons appearing from nowhere. It is a monumental task akin to tuning a radio dial across a continent's worth of static, searching for one faint, unknown station that may or may not be broadcasting. The sensitivity required is almost beyond belief. The experiment must be cooled to near absolute zero to eliminate thermal noise, and the amplifiers are so sensitive they operate at the quantum limit. This is the paradigm shift in action. We are no longer waiting for a rare, violent collision in the dark. We are listening with the most refined ears imaginable for the softest note in the universe's symphony. Could the answer to the cosmic ghost story be something this delicate, this subtle, a whisper woven into the fabric of space itself? But what if the ghost does not exist at all? What if the problem is not with our eyes, but with the very rulebook we use to interpret what we see? This is the most radical proposition in the hunt, one that challenges a cornerstone of physics. Perhaps there is no missing matter. Perhaps on the vast scales of galaxies, gravity itself simply works differently than Isaac Newton or Albert Einstein predicted. This idea is known as modified Newtonian dynamics, or MUND, and it begins with a single, elegant adjustment. Instead of invoking an invisible substance, it proposes that the force of gravity deviates from its familiar form when accelerations become incredibly small, a regime we almost never experience on Earth. Mordechai Milgrom, the physicist who first proposed MUND, framed it as an empirical discovery, noting that the data from galaxy rotation curves seemed to point to a new, simple law emerging at these low accelerations. The core idea is startling in its simplicity. In our solar system, where gravitational pulls are strong, Newton's laws work perfectly. But in the outer reaches of a galaxy, where a star feels only a whisper of a tug from the galactic center, the force of gravity might be slightly stronger than expected. This tiny boost, according to the WMAP formula, is enough to keep those fast-moving outer stars in orbit without any need for dark matter halos. It is as if you discovered that a familiar spring, when stretched only a millimeter, obeys one law, but when stretched a full meter, it subtly switches to a different, stronger kind of elasticity. The success of this simple formula at predicting the rotation curves of a wide variety of galaxies, from majestic spirals to tiny dwarf galaxies, is its greatest strength. For many of these systems, WMAP fits the observed motion of stars with remarkable precision using only the visible mass. Dwarf galaxies, with their faint, diffuse stars, become a particular triumph for WMAP, as they often pose challenges for standard dark matter models that require careful tuning of halo properties. Yet, for every success, there is a formidable challenge. The theory struggles mightily to explain the behavior of the largest structures in the universe. When scientists apply WMAP to massive galaxy clusters, the math consistently falls short. The observed gravitational lensing and the motions of hot gas within these titanic assemblies still require some form of unseen mass, often called cluster dark matter, to make the equations balance. Furthermore, the detailed pattern of the cosmic microwave background, that ancient baby picture of the universe, is exquisitely fit by the standard model that includes dark matter. Reproducing those precise wrinkles with a modified gravity theory alone has proven incredibly difficult. Proponents have developed more sophisticated, relativistic extensions of WMAP, like tensor vector scalar gravity, or TVS, which incorporate Einstein's framework and attempt to address these cosmic scale problems. But the path is fraught with complexity. This leads to a profound and contentious question at the heart of modern cosmology. Which is the more parsimonious solution, to invent an entirely new, invisible form of matter that fills the universe, or to modify a fundamental force that has been tested for centuries? The debate is not merely technical, it is philosophical, cutting to the core of how we build our understanding of reality. The persistence of this debate, with compelling evidence and deep puzzles on both sides, tells us something vital. The mystery of dark matter is not just a missing piece, it is a stress fracture in our foundational map of the cosmos, pushing us to look for answers in the most extreme environments imaginable. The cosmos is not a random scatter of stars, but a breathtaking tapestry woven from threads of light and shadow. Stretch your vision across billions of light years, and a pattern emerges, a vast cosmic web of brilliant galaxy clusters strung along dark, slender filaments separated by immense, empty voids. What force could have sculpted this architecture on such a monumental scale? The answer lies in the silent, gravitational blueprint of dark matter. In the earliest moments, the universe was a nearly smooth sea of energy and particles, but not perfectly smooth. Thanks to quantum fluctuations, tiny ripples of density existed, like gentle swells on a primordial ocean. Normal matter, the protons and electrons that would become stars, was too interactive, too hot. It was buffeted by the pressure of light, preventing those ripples from growing. Dark matter, however, was cold and collisionless. It felt only gravity. For this invisible substance, those tiny density ripples were everything. Slightly denser patches had slightly stronger gravity, pulling in more dark matter from the surroundings, making them denser still, in a powerful feedback loop that spanned cosmic time. These growing knots of dark matter became the gravitational wells, the scaffolds, into which normal gas could later flow, cool, and eventually ignite into the first stars and galaxies. To witness this epic story unfold, cosmologists do not use telescopes alone. They build universes inside supercomputers. Projects like the Illustris TNG simulation begin with the conditions of the early universe and the laws of physics, then set trillions of dark matter particles in motion, tracing their evolution over 13.8 billion years. The result is not a guess, it is a calculated destiny. As these simulations run, we watch a ghostly ballet of dark matter halos emerge, dance, and merge in a process called hierarchical structure formation. Small halos form first, drawn together by gravity to build larger ones, which in turn attract others, assembling the great clusters and filaments of the cosmic web we observe. The most compelling validation comes when scientists compare these simulated dark matter maps to the real, observed distribution of millions of galaxies from sky surveys. The match is stunning. The large-scale structure of our universe, the placement of great walls and vast empty regions, is reproduced with remarkable fidelity by simulations that treat dark matter as a cold, collisionless fluid. This is perhaps the strongest evidence we have for its physical reality. How can something we have never directly touched predict the architecture of the cosmos with such precision? The success of these cosmic simulations presents us with a profound paradox. We can map dark matter's gravitational influence across the largest distances. We can use it to accurately build a universe in a computer, and yet the fundamental particle or field responsible for it all continues to hide from our most sensitive detectors. We know the ghost's handiwork intimately. We have seen its shadow cast across the sky, but its face remains a mystery. This gap between large-scale proof and small-scale silence is the defining tension of the hunt, pushing us toward ever more creative and extreme possibilities for what, or even where, this elusive substance might be. The cosmic web is a masterpiece of dark matter's design, yet its finest details reveal a troubling inconsistency. If cold dark matter is so perfectly successful on the grand scale, sculpting the vast filaments and clusters of the universe, why does it seem to stumble when we zoom in on the neighborhood of our own galaxy? The predictions born from those magnificent supercomputer simulations begin to fray at the edges, presenting a series of puzzles known collectively as the small-scale crises. The first and most famous is called the missing satellites problem. When cosmologists run simulations of a Milky Way-like galaxy emerging within a cold, dark matter universe, they predict not just a few dozen satellite dwarf galaxies orbiting it, but hundreds, even thousands of them. The gravitational scaffolding is so rich and lumpy that it should spawn a bustling swarm of tiny dark matter halos, each a potential home for a small galaxy. Yet when we look up, we only confidently see about 60 such satellites around our own galaxy. Where are all the rest? This discrepancy forced a hard look at our assumptions. Perhaps the smallest halos are indeed out there, but they are so faint, so devoid of stars that they remain invisible to our surveys, truly dark galaxies. Or perhaps, as some astrophysicists argue, the process of forming stars within these tiny halos is so inefficient, so easily quenched by the harsh light of the first massive stars or the heat from supernova, that most simply never light up at all. This introduces a key tension in the field, often summarized by researchers as a debate between dark matter physics and baryonic physics. Are the missing satellites a clue about the nature of dark matter itself, or are they just a testament to the messy, complex, and poorly understood ways that normal matter gathers and ignites within its invisible cages? The second crisis cuts even deeper to the very heart of these dark matter halos. Simulations consistently produce halos with density profiles that have a steep central peak, a sharp cusp of incredibly dense dark matter. This is a clean gravitational prediction, yet observations of many real dwarf galaxies, like the Draco dwarf spheroidal that orbits the Milky Way, suggest something different. Their stars move in ways that indicate the dark matter within them is more smoothly distributed, forming a constant density core rather than a sharp cusp. It is as if the very center of these dark matter halos has been somehow scooped out. How could this happen? One provocative solution points back to the fury of ordinary matter. Intense bursts of star formation in the early life of a small galaxy could have triggered powerful supernova, whose explosive energy might have pushed and churned the gaseous core, and through gravity, dragged the dark matter outward, flattening the central cusp into a soft core. This is the baryonic physics argument in full force, suggesting that the very stars we use to measure dark matter may have reshaped it. But if star formation alone cannot explain all the observed cores, the fault may lie with dark matter's own nature. This has led to fascinating alternative models. What if dark matter is not completely cold and collisionless? The self-interacting dark matter model proposes that dark matter particles can occasionally scatter off one another, like billiard balls in the dark. This gentle self-interaction would transfer heat from the outer parts of a halo into the center, puffing up the dense cusp into a smoother core over cosmic time. Alternatively, warm dark matter, made of particles that were born moving at a significant fraction of light speed, would have washed out the smallest scale structures from the beginning, naturally reducing the number of tiny halos and potentially producing softer cores. Each idea leaves a distinct fingerprint on the structure of the universe that future observations could trace, so we are left with a pivotal, reflective question. Are these small-scale crises cracks in the foundation of the cold dark matter paradigm, or are they merely gaps in our understanding of how the luminous world interacts with the dark one? The answer for now is that they are both. They are the precise points of tension where our knowledge is being stress-tested, where the elegant simplicity of the large-scale model meets the chaotic, feedback-driven reality of galaxy formation. This uncertainty is not a weakness in the scientific process, it is the engine of it. These puzzles drive relentless innovation, pushing theorists to refine their models and observers to peer deeper into the faintest dwarfs with next-generation telescopes. They remind us that the ghost we hunt may not be a simple, monolithic entity, but a substance with hidden layers and subtle properties waiting to be revealed. The search is narrowing not on where to look, but on how dark matter truly behaves in the intimate, complex nurseries where galaxies are born. Perhaps the ghost is not a particle, but a trapdoor. A shadow so deep not even light can climb out. One of the most dramatic ideas in the hunt proposes that dark matter is not a new substance at all, but something we already know, born under the most extraordinary conditions imaginable in the first fleeting moments of creation. These are primordial black holes. Think of the universe not a second after the Big Bang as a seething, ultra-dense cauldron. Within that churning plasma, random quantum fluctuations could have created pockets of matter so intensely dense they collapsed directly under their own gravity, stitching tiny knots of infinite curvature into the fabric of space-time itself. Unlike the stellar black holes we know, forged from the death throes of massive stars, these would be primordial, artifacts of the universe's violent birth. Their appeal is profound in its simplicity. As the late Stephen Hawking, who helped pioneer their study, once noted, they represent a minimal solution. If dark matter is made of black holes, we need no new particles, no exotic fields. We have gravity alone, in its most extreme form, doing the work of sculpting the cosmos. These black holes could span a staggering range of sizes. Some might be as small as an asteroid, with the mass of a mountain compressed into a space narrower than an atom. Others could rival or exceed the mass of our Sun, yet remain as dark and silent as their smaller siblings. They would drift through the galaxy like invisible icebergs in a dark sea, their only signature the warp in space-time they carry with them. We have already seen hints of their possible presence through a phenomenon called gravitational microlensing. When one of these compact, dark objects passes directly between us and a distant star, Its gravity acts as a temporary lens, focusing the star's light and causing it to briefly brighten before fading back to normal. Surveys like the optical gravitational lensing experiment have recorded hundreds of such unexplained events, short flashes that could be the footprints of unseen masses moving through the galactic halo. For a time, this was a thrilling possibility, but science advances by closing doors as much as opening them. The idea of primordial black holes as the dominant dark matter has faced a gauntlet of constraints that have narrowed the possible hiding places to just a few slim windows. The cosmic microwave background provides one powerful limit. If too many large black holes existed in the early universe, their gravity and any material falling into them would have injected extra energy, distorting the pristine pattern of the afterglow in ways we do not observe. The survival of delicate ancient structures like dwarf galaxies and wide binary star systems places another tight constraint. A swarm of asteroid-mass black holes would act like cosmic cannonballs. Over billions of years, their gravitational nudges would disrupt or tear these fragile systems apart. Perhaps the most exciting new constraint comes from the realm of gravitational waves. When the LIGO Observatory made its first historic detection in 2015, it recorded the merger of two black holes, each about 30 times the mass of the Sun. The immediate, electrifying question was, where did these surprisingly heavy black holes come from? Could they be primordial remnants of the first second, and thus part of the dark matter? Subsequent observations have made this less likely. The rate of such mergers, the spin of the black holes involved, and their contribution to the overall mass budget of the universe suggest they cannot account for more than a small fraction of the total dark matter. They are fascinating in their own right, but they are not the main character in this story. So what remains? The constraints have carved out only a few narrow mass ranges where primordial black holes could still, in principle, constitute all the dark matter. One window exists for black holes around the mass of a large asteroid. Another, more speculative window exists for truly enormous ones, tens of thousands of times more massive than the Sun, though these would be rare and would have left other scars on galaxy formation. The hunt, therefore, has become a search within these specific bands. Could dark matter be something we already understand, just born under extraordinary conditions? This idea elegantly connects the physics of the very large, the structure of galaxies, to the physics of the very small, the quantum fluctuations of the infant universe. It is a reminder that the answer may not require inventing a new fundamental ingredient, but rather recognizing an old one playing a hidden role on the grandest stage of all. Neutrinos are the universe's ultimate ghosts, real particles that pass through our planet by the trillions every second, yet they leave almost no trace. For a time, they seemed a perfect candidate for the missing mass. They are elusive, neutral, and abundant, a product of nuclear reactions in stars and the Big Bang itself. Yet despite their ghostly credentials, cosmologists have definitively ruled them out as the primary component of dark matter. The reason lies not in what they are, but in how they move. Neutrinos have an astonishingly tiny mass, so small we have not yet precisely measured it. This minuscule weight means they were born moving at velocities approaching the speed of light, a category physicists call hot dark matter. And in cosmology, temperature is destiny. To understand why, we must watch the early universe through the lens of gravity's patient pull. In that primordial soup, dark matter's job was to create the gravitational seeds for galaxies. Cold dark matter, sluggish and slow, could clump together easily, forming the dense knots that would later attract gas. Hot dark matter, like neutrinos, would have been racing far too fast to be captured by these tiny gravitational wells. They would have streamed freely across the universe, smoothing out the small-scale ripples before they could grow. As one particle cosmologist explains, the cosmic microwave background and the distribution of galaxies act as a forensic record, and the evidence is clear. If neutrinos made up the bulk of dark matter, their high velocity would have washed out the fine-scale structure we see. Galaxies would be far more diffuse, and the cosmic web would lack the rich, filamentary detail revealed by our telescopes and simulations. The data places a firm upper limit on the total mass of all neutrino species. While they do contribute a sliver to the cosmos's mass budget, that sum is far too small, a fraction of a percent, to account for the 27% attributed to dark matter. This exclusion is not a failure, but a triumph of precision cosmology. It demonstrates the power of using the universe itself as a laboratory. By comparing the observed large-scale structure with detailed simulations, scientists can distinguish between the cosmic fingerprints of hot and cold dark matter. The key concept is free streaming length. The average distance a particle travels before its motion is redirected by gravity. For a fast-moving neutrino, this distance is enormous on the scale of superclusters of galaxies. This is like trying to build a sandcastle with dry, fine sand in a strong wind. The grains simply blow away before they can stick together. Cold dark matter, in contrast, has a minuscule free streaming length, allowing it to gather into the dense, granular clumps that become the building blocks of galaxies. So we are left with a refined and sharper question. How does crossing a known, elusive particle off the list actually bring us closer to an answer? This rigorous process of elimination is the engine of the hunt. Each excluded possibility, from heavy WIMP to lightweight neutrinos, carves away territory on the map of the unknown, forcing the solution into a narrower, more defined space. The ghost we seek is not just dark, it is also cold, slow, and profoundly patient, a substance that settled into the fabric of the cosmos to shape it from the shadows. Deep beneath the Swiss-French border, protons race in opposite directions through a ring of chilled metal 27 kilometers long. Within the caverns of the Large Hadron Collider, these particles are whipped to energies unimaginable on Earth, then steered into a head-on collision. In these fleeting instants, the conditions of the early universe are recreated in a microscopic fireball, a place where the fundamental rules of reality are laid bare. This machine, the most powerful ever built, is not just a microscope for the small. It is a forge for the unknown, and physicists have long hoped it could be the place where dark matter is finally made. The strategy is as bold as the machine itself. If dark matter particles exist and interact with the ordinary world through any force, even the feeble weak force, then slamming ordinary protons together with enough violence could, in theory, conjure them into existence from the raw energy of the collision. But there is a profound catch. If these particles are as ghostly as the cosmological evidence suggests, they would immediately flee the scene of their own creation, passing through the layers of the massive detectors without a trace. So how do you look for something that refuses to be seen? You look for its absence. You hunt for the ghost shadow. When two protons collide, the total momentum going into the event is, by the laws of physics, zero. All the energy and movement of the resulting spray of particles must balance out. But if an invisible particle is born and carries away a chunk of that momentum, the visible debris will appear lopsided. This imbalance, this missing transverse momentum, becomes the signature of the invisible. It is like watching a billiard break where one of the balls shoots off the table into the dark. You do not see the ball itself, but you know it must be there because the motion of all the other balls does not add up. Inside the cathedral-scale detectors named Atlas and CMS, this search for momentum that has gone missing is one of the most intense pursuits. Physicists comb through billions of collision events, searching for those with a distinctive pattern, a spray of known particles called jets, recoiling against a large amount of energy that simply vanishes. An event display from one such search is a work of abstract art that tells a story of profound mystery. You see the colorful tracks of charged particles curving in magnetic fields, the blocks representing deposits of energy from neutral particles, and then a large, empty wedge on the display, a silent void pointing in the direction where nothing was recorded. That void is where the answer might be hiding. The challenge is monumental. The universe is noisy, and so is a proton collision. Standard model processes, like the production of a Z boson that decays into neutrinos, also produce genuine missing momentum, since neutrinos are nearly as ghostly as dark matter. Distinguishing a potential dark matter signal from these known backgrounds requires exquisite precision and statistical power. As one researcher on the CMS experiment explains, it is a process of extreme subtraction. We must understand every conceivable way our known physics can mimic the signal, and only when we have accounted for all of it can we look at what remains. The LHC probes a different frontier than the underground laboratories. Direct detection waits for dark matter from the galactic halo to drift through its sensors. The collider attempts to manufacture it on the spot, probing interactions and mass ranges that might be completely inaccessible to the passive experiments. Some theories suggest dark matter could interact with ordinary matter through a new, unknown force, carried by a hypothetical mediator particle. The collider could produce this mediator, which would then decay into dark matter particles, leaving that same telltale missing energy signature. Over years of operation at ever higher energies, the teams have performed hundreds of such analyses, each carving out a new region of possibility. The result, so far, echoes the quiet from the deep underground. No unambiguous signal has emerged. The detectors have seen nothing in the void that cannot be explained by the known laws. This relentless null result is itself a form of discovery, pushing the possible properties of dark matter into more extreme territory. It tells us that if dark matter is a particle that interacts with ordinary matter, that interaction is even weaker, or the particle is heavier than many hopeful models predicted. So we are left with a question that tests the limits of our ingenuity. What if dark matter is so weakly coupled to our world that even recreating the furnace of the early universe cannot produce it in a way we can discern? The collider's silence is not an end but a guidepost, forcing us to consider that the ghost might be even more estranged from our reality than we dared to believe. The heart of the Gran Sasso Mountain in Italy is a silent world of science. Shielded by over a mile of solid rock, the Laboratory Nazionale del Gran Sasso houses experiments that listen for whispers from the cosmos. Among them, one has produced a tantalizing and deeply controversial signal for more than 2 decades. The Dharma/Libra experiment does not use liquid xenon or cryogenic crystals. Its core is an array of highly pure sodium iodide crystals, chosen for their unique sensitivity. Since the late 1990s, this experiment has recorded a peculiar rhythm. The rate of tiny flashes of light within its detectors rises and falls with a precise annual cycle, peaking every June and dipping every December. The collaboration behind the experiment, a dedicated international team, interprets this as a direct signature of dark matter. They call it the annual modulation. The hypothesis is elegant. Our solar system orbits the center of the Milky Way, but so does the vast halo of dark matter that engulfs it. As Earth journeys around the Sun, its motion through this halo changes direction relative to the galaxy's rest frame. In June, Earth's orbital velocity adds to the Sun's motion through the halo, so our planet is effectively plowing into the dark matter wind. In December, it is moving with the wind. This should cause the apparent flux of dark matter particles to vary by a few % over the year, creating a gentle, sinusoidal wave in the data. The Dharma team's published results show exactly that, a clean, persistent wave that has now cycled over 20 times. One researcher from the collaboration has stated with conviction that the signal is there and it matches the predicted phase and period perfectly. They believe they are seeing the Earth's motion through the galactic dark matter sea. Yet this claim stands in stark isolation at the center of one of the most heated debates in modern physics. No other experiment in the world has been able to confirm this signal using the same sodium iodide technology. Skeptical scientists point to a long list of potential alternative explanations, each meticulously investigated. Could it be seasonal variations in cosmic ray muons, even deep underground? What about subtle temperature or humidity changes in the laboratory over the year that might affect the sensitive electronics? Perhaps it is a seasonal fluctuation in radon gas emanating from the surrounding rock, or even an intrinsic property of the sodium iodide crystals themselves. Every proposed background has been scrutinized, and the DAMA collaboration maintains they have accounted for them all. To resolve the standoff, other groups have built experiments designed specifically to test DAMA claim. The Cosine 100 experiment in South Korea and the ANICE experiment in Spain also use sodium iodide crystals, operating under similar deep underground conditions. After collecting years of data, their results have been clear. They do not see the modulation signal. This contradiction is not a simple yes or no. It is a profound puzzle about the nature of the signal itself. Could DAMA be seeing a rare, unexpected interaction that depends on minute differences in crystal purity or the specific methods of data analysis? The graph of DAMA data is haunting. It shows a scatter of data points over time, but through them, a smooth, undulating sine wave is clearly visible, a ghostly heartbeat that refuses to fade away. This forces a critical question for every scientist in the field. When does a persistent anomaly, unconfirmed by others, become a compelling clue rather than a stubborn artifact? The DAMA signal represents the human dimension of the hunt, a reminder that discovery is not just about data, but about interpretation, scrutiny, and the immense challenge of hearing a true signal in a universe full of noise. It is a mystery that endures, a single, unexplained rhythm in the dark that continues to challenge everything we think we know. The forest of possibilities is growing darker and more complex. For decades, the search followed two main trails, the well-trodden path of heavy WIMP and the more subtle track of wave-like actions. Yet as those trails have led to profound silence, theorists have been forced to light torches and venture into the undergrowth, mapping a bewildering array of new speculative avenues. This is the theoretical crossroads where the lack of a detection is not a stop sign, but an invitation to imagine more wildly. As one physicist framed it, we are no longer looking for a needle in a haystack, we are questioning whether we are even in the right field. The landscape now includes candidates with names that sound like characters from a cosmic fantasy: sterile neutrinos, fuzzy dark matter, SIMP, and Q balls. Each is born from a desire to solve a specific piece of the puzzle. Sterile neutrinos, for instance, are hypothetical heavier cousins to the ordinary neutrino that interact only through gravity. They could be warm dark matter, potentially explaining the paucity of small satellite galaxies while still forming the large-scale cosmic web. Then there is fuzzy dark matter, an idea that takes the action concept to an extreme. Here, the particles are so incredibly light, billions of times lighter than an electron, that their quantum wave nature becomes dominant on the scale of entire dwarf galaxies. This could naturally create the soft, core dark matter distributions we seem to observe, as the quantum pressure prevents the matter from collapsing into an infinitely dense point. Imagine it as a galaxy filled not with discrete particles, but with a single, coherent quantum fluid, humming at a frequency too low for us to hear. On the opposite end of the spectrum are SIMP, strongly interacting massive particles. These candidates turn the WIMP paradigm on its head. Instead of interacting weakly, they interact strongly with each other, but barely at all with normal matter. This self-interaction could solve the core cusp problem by allowing dark matter to scatter and smooth itself out within halos. yet their aloofness from our world makes them nearly impossible to detect directly. This leads to one of the most profound expansions of the theory, the concept of a complete dark sector. What if dark matter is not a lone particle but part of a rich, hidden universe operating in parallel to our own? This shadow realm could have its own forces mediated by dark photons and its own families of particles, some that are dark matter and others that are not, all interacting under rules we are just beginning to guess. Within this framework, even more exotic structures become possible, like cue balls, stable blobs of coherent field that could behave like macroscopic dark matter objects. Each theoretical fork in the path suggests a different experimental strategy. Searching for a dark photon, for instance, might involve looking for slight anomalies in the way light bends or how particles behave in powerful magnetic fields, a whisper of interaction between our sector and the dark one. The sheer diversity of ideas presents a fundamental question. Are we, as explorers, limited more by our own imagination, or by the universe's stubborn reluctance to reveal its deepest architecture? This theoretical explosion is not a sign of confusion, but of a field in vibrant, creative ferment. It means the ghost we seek may wear a mask we have not yet dreamed of, and that the final answer will likely be stranger than any single path we have walked so far. Silence can be the loudest result of all. The persistent non-detection of dark matter across decades of searching is not a story of failure, but a powerful form of guidance. Each experiment that comes up empty hands us a crucial piece of the puzzle, a map of where the ghost cannot be. These are called exclusion limits, the rigorously defined territories of mass and interaction strength that our most sensitive instruments have now ruled out. As a lead scientist from the XENONnT collaboration has expressed, there is a deep pride in achieving such profound silence, in pushing the background noise so low that the absence of a signal becomes a world-leading result. It means we have listened more carefully than anyone before. To understand these limits, picture a vast two-dimensional map. One axis represents the possible mass of a dark matter particle, from lighter than an electron to heavier than a planet. The other axis represents how strongly it might interact with normal matter. Every direct detection experiment, after years of patient listening, can draw a line on this map. The area above that line, representing stronger interactions, is now excluded. If dark matter existed there, the experiment would have seen it. The relentless progress of technology has pushed this exclusion line downward year after year, like a slowly descending curtain, shrinking the possible hiding places into an ever narrower band of extreme weakness. The latest results from experiments like XENONNT have pushed the sensitivity to such incredible levels that if dark matter is a typical WIMP, it must interact more feebly than we ever anticipated, or it must reside in a mass range we have only begun to explore. This cartography of the unknown is a collaborative effort across all fronts of the hunt. The limits from underground direct detection experiments are cross-checked against the null results from the Large Hadron Collider, which has ruled out vast territories where dark matter could be produced, and from indirect searches, which have found no unambiguous annihilation glow. Together, they create a triangulated cage of constraints. If you were to look at a plot of these exclusion curves from the past 20 years, you would see a dramatic visual story. The wide open spaces of possibility from the early 2000s have been carved away into a thin sliver of remaining parameter space, a frontier that now demands even more ingenious tools to explore. This forces a pivotal, almost philosophical reflection. Is the absence of evidence a form of evidence itself? In the rigorous world of physics, the answer is a definitive yes. This meticulous process of elimination is the engine that drives science forward when a mystery proves stubborn. It tells us our initial, elegant guesses were too simple, that the universe is under no obligation to conform to our sense of mathematical beauty. The null results are not a wall, they are a signpost redirecting the hunt toward more creative and exotic possibilities, whispering that the ghost is stranger and perhaps more fascinating than we first dared to dream. The sky is not just a map of stars, it is a canvas of unexplained light. Certain glimmers and shadows observed by our most powerful telescopes might be the faintest brushstrokes of dark matter's hidden hand. These are astrophysical anomalies, phenomena that stubbornly resist explanation by our catalogue of known celestial objects and processes. For the dark matter hunter, they represent a thrilling, if perilous, frontier where a cosmic ghost might have accidentally left a fingerprint. Astronomers studying these edge cases often speak of a necessary and profound caution. The universe is full of ordinary wonders we do not yet fully understand, so leaping to a dark matter explanation for every oddity is a trap. Yet, a few mysteries persist with such clarity that they demand we at least consider the extraordinary. One of the most puzzling is the unexpected transparency of the universe to the most energetic gamma rays. These photons, trillions of times more energetic than visible light, should have a limited journey. According to our models, they should collide with the faint background glow of starlight permeating space, annihilating to create electron pairs and thus being absorbed over cosmic distances. Yet when telescopes like the Magic Array or the Fermi satellite observe distant blazars, they often see these ultra-high energy gamma rays arriving in greater numbers than expected. It is as if the universe is more clear, more empty than it should be. One provocative explanation points to dark matter. If these gamma rays were interacting with the invisible halo of a dark matter particle, perhaps converting into other particles along the way, it could alter their apparent journey, making the cosmos seem more transparent. It is a subtle effect, a potential shadow cast by the ghost on the most violent light. Another set of clues comes from the quietest neighborhoods in the cosmos, the dwarf spheroidal galaxies. These faint, diffuse collections of stars are considered pristine dark matter laboratories, as they contain very little of the messy gas and star formation that can complicate signals in larger galaxies. Some of these dwarfs show curious internal motions or an unexpected distribution of stars that even detailed dark matter halo models struggle to fit perfectly. Furthermore, when scientists look at these dwarfs with gamma-ray telescopes, a few have shown faint, unexplained excesses of emission. While none have reached the threshold of discovery, these persistent whispers keep attention focused on these dark matter-dominated realms as prime hunting grounds for an indirect signal. Perhaps the most debated specific anomaly in recent years was a faint line in the X-ray spectrum. Around 2014, two independent teams analyzing data from the XMM Newton Space Telescope reported a curious spike of X-ray emission at an energy of 3.5 kilo-electron-volts or keV. This line was seen emanating from the hot gas in massive galaxy clusters like Perseus and even from the Andromeda Galaxy. The excitement stemmed from a compelling theoretical match. This precise energy could be the signature of a sterile neutrino, a hypothetical dark matter candidate, decaying into an ordinary neutrino and a photon. The graph of the data showed a small but persistent bump rising above the smooth curve of thermal emission from hot gas, a tiny needle in a haystack of X-ray noise. For a time, it seemed like a potential breakthrough, a direct spectral line from the dark sector itself. However, the scientific process is ruthlessly thorough. Other researchers scrutinized the data, proposing alternative astrophysical origins. Could the line be produced by exotic plasma physics, or by sulfur ions undergoing a specific transition in the intense heat of the cluster? Subsequent observations with other telescopes, like Japan's Hitomi satellite, which had the exquisite resolution to study the Perseus cluster, failed to confirm the line before the satellite was lost. The current consensus leans toward a more mundane astrophysical explanation, but the case is not entirely closed. It remains a masterclass in the challenge of this hunt. How do we distinguish between a new astrophysical source and a particle physics breakthrough? The distinction requires multiple lines of evidence. A true dark matter signal would appear consistently across many different types of objects, all with high concentrations of dark matter, like galaxy clusters, dwarf galaxies, and the Milky Way center. It would have the same energy everywhere. An astrophysical line might appear only in specific environments with the right temperature and chemical composition. Other curiosities dot the celestial map, like the Fermi bubbles, enormous lobes of gamma-ray emission ballooning from the center of our Milky Way. Their origin is still debated, with explanations ranging from an ancient outburst from the supermassive black hole to a prolonged period of star formation. A dark matter annihilation signal is a less favored but still discussed possibility, especially for a uniform glow that might overlay these structures. These tantalizing hints, each requiring years of patient observation and analysis, are what keep the hunt alive and multidimensional. They remind us that the answer may not arrive with a single, dramatic bang in an underground detector, but as a pattern of light slowly deciphered across the vast canvas of the night. Deep beneath the surface, a new generation of cathedrals is being planned. These are not monuments of the past, but instruments of the future, designed to listen for a whisper, so faint it currently hides beneath the murmur of the universe itself. The next phase of direct detection is a monumental leap, envisioning detectors 100 times more sensitive than today's most advanced machines. We are moving from the quiet rooms of today to the silent temples of tomorrow. At the forefront of this vision is Darwin, a proposed ultimate observatory using liquid xenon on a scale never before attempted. Imagine a vessel holding not 1 or 2 tons of purified xenon, but potentially 50 tons or more, a vast, dark lake waiting for a single, impossible ripple. As a lead scientist on the project's design study explains, the goal is to create a background-free environment, a place where any signal that emerges cannot be mistaken for anything but new physics. Alongside it, proposals like Argo envision similar scales using liquid argon, another noble element with unique properties that could cross-check any potential discovery. The significance of these mega-experiments goes beyond simply scaling up. They aim to probe a frontier known as the neutrino floor. This is not a wall, but a fundamental horizon. As detectors become more sensitive, they will eventually become vulnerable to a new kind of background, the coherent scattering of neutrinos from the Sun, from nuclear reactors, and even from the Big Bang. These neutrinos, also ghostly particles, will interact with atomic nuclei in a way that perfectly mimics the signature of certain dark matter particles. Once we reach that sensitivity, distinguishing a dark matter signal from a neutrino becomes the ultimate challenge. To even approach this horizon, a revolution in engineering and purity is required. Every component must be reimagined. The vessels themselves will be forged from new alloys with unimaginably low radioactivity. The xenon or argon must be purified to levels that make today's standards seem crude, filtering out even a single rogue atom of radioactive krypton or argon-39. Photon sensors will need near-perfect efficiency, capturing every precious photon of light from a potential interaction. And the algorithms that analyze the data will need to be sophisticated beyond current comprehension, learning to distinguish the subtle differences in the pattern of light and charge that might separate a neutrino's touch from a dark matter particle's nudge. The conceptual designs for these experiments are breathtaking in their ambition. They depict cavernous spaces housing not just the detector, but nested layers of shielding, purification plants the size of buildings, and cryogenic systems of staggering complexity. This is science on the scale of an international particle collider, requiring global collaboration and decades of sustained effort. The timeline stretches toward the middle of the century, with goals set not just for detection, but for definitive measurement to study the properties of dark matter if we finally catch it. This future is fraught with both profound promise and a deep philosophical peril. It forces us to ask a question that hangs over the entire endeavor. What if we build the perfect detector, push our sensitivity to the very edge of the neutrino floor, and still see nothing but the expected cosmic chatter? That silence would be louder than any discovery. It would tell us with devastating clarity that dark matter's interaction with our world is not just weak, but non-existent in the ways we have imagined. It would mean the ghost is not merely shy, but fundamentally deaf to everything but gravity. This possibility is the shadow that gives the quest its gravity. To commit to these monumental projects is to accept that the greatest discovery might be learning definitively where the answer is not, forcing a complete reimagining of the cosmos. It is a testament to humanity's enduring commitment to the puzzle, a willingness to spend generations and vast resources chasing a shadow, knowing that the pursuit itself, the mapping of our own ignorance, is a form of enlightenment. While underground labs grow larger and quieter, our eyes on the sky are also undergoing a revolution. A new generation of observatories is rising, instruments with such profound sensitivity they promise to hear the faintest echoes of dark matter's hidden activities. This is the next chapter of indirect detection, where we are no longer just scanning the heavens, but learning to read their most subtle signatures. The strategy is multi-messenger astronomy, the coordinated search for dark matter's fingerprints across the entire spectrum of cosmic signals, from the highest energy gamma rays to the most elusive neutrinos. As one astrophysicist working on these projects describes it, we are building a net of different meshes, hoping that what slips through one will be caught by another, until the shape of the ghost becomes clear. Leading this charge is the Cherenkov Telescope Array, or CTA. This is not a single telescope, but a global network of over 100 extremely large telescopes split between sites in Chile and the Canary Islands. Instead of collecting light directly, these instruments watch for the faint blue flashes of Cherenkov radiation, created when ultra-high energy gamma rays from space strike our atmosphere and produce a cascade of secondary particles. CTA will see the universe in very high energy gamma rays with 10 times the sensitivity and 4 times the resolution of any existing facility. For dark matter, this is a game changer. It will perform deep, long-term observations of the most promising targets, like the dense core of our Milky Way and nearby dwarf spheroidal galaxies. Scientists will not just look for an excess of gamma rays, they will search for a specific spectral shape, a bump or a line at a particular energy that cannot be explained by pulsars or cosmic ray interactions. They will also study the morphology, the spatial distribution of any signal. A dark matter annihilation glow should follow the predicted shape of the dark matter halo, smooth and extended, unlike the point-like sparkle of a pulsar. CTA could, for the first time, provide a detailed map of dark matter's potential self-destruction. In another part of the electromagnetic spectrum, the James Webb Space Telescope is already reshaping our understanding of dark matter's cosmic playground. While not a dark matter detector itself, Webb's unparalleled power to peer into the early universe and study faint, local dwarf galaxies provides critical context. By precisely measuring the motions of stars within these pristine dark matter dominions, Webb helps astronomers refine the gravitational maps of their halos, telling us exactly where to look for indirect signals. It can also study the earliest galaxies, probing how dark matter guided their formation, offering another test for our models. Meanwhile, beneath the Mediterranean Sea, a colossal neutrino telescope is taking shape. KM3NET will consist of thousands of optical sensors anchored to the seafloor, turning several cubic kilometers of clear, deep water into a neutrino detector. Neutrinos, like dark matter, are cosmic ghosts, but when one rarely interacts with the water, it produces a flash of light that the sensors can trace. KM3NET will scan the southern sky, including the galactic center, for high-energy neutrinos that could be the products of dark matter annihilation. A coincident signal of neutrinos and gamma rays from the same region of space would be a smoking gun, strong evidence pointing to a common, exotic source like dark matter. The power of this multi-messenger approach lies in cross-verification. A bump in gamma rays alone could be an unknown astrophysical object. A surge of neutrinos alone could be a fluke. But if both messengers arrive together from a dark matter-rich region, with energies that tell a consistent story, the case becomes compelling. Scientists create sophisticated simulations to prepare for this moment, generating mock data that shows how a dark matter signal might rise from the background noise across these different channels. The graph is a thing of beauty, a smooth curve of astrophysical background, and then, from a dwarf galaxy's direction, a small but statistically significant excess of events at a precise energy, appearing in both the gamma-ray and neutrino catalogs. This collaborative, multi-pronged search represents a fundamental shift in our strategy. We are no longer hoping for a single, lucky strike. We are systematically constructing a profile of the ghost by listening to every way it might disturb the medium of our universe. These new observatories expand our sensory reach to its absolute limit, asking a profound question of the cosmos. Will the universe's most violent and energetic phenomena, the deaths of stars and the hearts of galaxies, finally become the tools that illuminate its most secretive and silent component? The quiet hum of a possible universe is getting louder. While other searchers listen for collisions, the hunt for Axions is an exercise in exquisite tuning, a quest to hear a single, pure note in a cosmic static that spans continents. What began as a tabletop experiment has now evolved into a major international endeavor, scaling up to confront the sheer vastness of the unknown. The core challenge is stark. We do not know the Action's mass, which translates directly to the frequency of the microwave photon it might become. The possible range is enormous, a bandwidth of cosmic proportions. Searching for it is like trying to find one unknown radio station somewhere across the entire radio dial of a planet, listening to only one tiny slice of static at a time. The original Axion dark matter experiment, ADMX, pioneered the Haloscope method. It uses a powerful magnet and a tunable resonant cavity, a metal chamber that amplifies a specific frequency like the body of a violin amplifies a single string's note. For years, ADMX has meticulously scanned the lower end of the possible mass range, achieving the sensitivity needed to hear the Action's whisper if it sings within those specific bands. But the higher mass ranges corresponding to higher frequencies remained out of reach. Their cavities were simply too small to resonate at those pitches. Now the next phase is here. ADMX Extended Frequency Range, or ADMX EFR, is designed to break this barrier. It will employ a new set of smaller, more complex cavities and advanced quantum amplifiers to push into uncharted territory. As one experimentalist working on the project explains, it is a leap in engineering, requiring us to maintain incredible sensitivity while tuning across a much wider sonic landscape. We are essentially building a more versatile musical instrument to play the universe's hidden song. Alongside this, other innovative approaches are emerging to cover the spectrum faster. The organ experiment in Australia is a haloscope optimized for a specific higher mass range. And then there is MADMAX, a European collaboration proposing a radically different design. Instead of a single cavity, MADMAX plans to use a stack of precisely engineered dielectric disks, like a series of specialized lenses placed in a strong magnetic field. When an action passes through, the disks would collectively boost the conversion into a detectable microwave signal, allowing it to probe masses far higher than any cavity could reach. This is the scaling challenge in action, moving from singular instruments to orchestrated arrays. Complementary to the Haloscope is the Haloscope concept. If actions exist, they should also be produced in the core of our Sun. A helioscope, like the CAST experiment at CERN, points a powerful magnet at the Sun, acting as a telescope for these solar-borne actions, trying to convert them into X-rays that detectors can catch. It is a different vantage point, searching not for the cold dark matter halo, but for actions freshly minted in our local star. Beyond these, physicists are exploring even more ingenious methods. Some proposals use nuclear magnetic resonance, the same principle as an MRI scanner, to look for the subtle influence of the action field on the spin of nuclei in a laboratory sample. Others look to laboratory astrophysics, using precise measurements of the behavior of light in magnetic fields to catch infinitesimal deviations that could signal an action's presence. Each technique is a different kind of ear, listening for the ghost in a distinct way. The collective effort resembles the slow, deliberate tuning of an action dark matter radio. We are turning the dial with immense care, spending months or years listening to each micro-frequency, knowing that the next click of the tuner could bring in the station we have sought for decades. This leads to a reflective question at the heart of this technological marathon. Could the discovery come not from scaling a known method, but from a radically different approach no one has yet conceived? The action frontier is a testament to human ingenuity, a blend of precision engineering on the knife edge of quantum limits and a patience that spans generations, all aimed at hearing the faintest note in the silence. A digital universe is born from a line of code. Inside the world's most powerful supercomputers, cosmologists are not just modeling dark matter, they are growing entire galaxies from scratch, letting the laws of physics play out over billions of virtual years. These are cosmological simulations like Illustris, Eagle, and Fire, and they have become our most sophisticated testbeds for the dark matter mystery. They start with the primordial soup of the early universe, seeded with the tiny density fluctuations we see in the cosmic microwave background. Then they set in motion trillions of particles representing dark matter, and alongside them, a fluid representing the normal baryonic gas. The magic and the immense challenge lies in what happens next. The simulations must account for the entire chaotic life cycle of ordinary matter, processes too complex to calculate directly for every atom. Gas must cool and collapse under gravity, ignite into stars, and then those stars must explode as supernova, blasting energy and heavy elements back into the virtual void. This is called baryonic feedback, and it is the wild card in the cosmic deck. For years, the small-scale crises, like the missing satellite problem and the cusp core tension, seemed like flaws in the cold dark matter model. But these new simulations reveal something profound. The violent outbursts from stars and black holes are not just side effects, they are powerful sculptors. When a burst of star formation triggers a wave of supernova in a small dwarf galaxy, the explosive energy can push the surrounding gas around. That moving gas, through its gravity, can drag and pull on the dark matter itself, gradually smoothing out the predicted dense cusp into a shallower, flatter core. It is a cosmic dance where the luminous world reshapes the dark one. Computational astrophysicists describe this as a delicate balancing act. You are simulating a volume of space hundreds of millions of light years across, yet you need to capture details on the scale of individual supernova. Since that is computationally impossible, scientists create subgrid models, sophisticated recipes based on real physics that approximate the large-scale effects of these small, violent events. Getting these recipes right is an art form, constantly refined by comparing the virtual universes to our real one. The results are breathtaking visualizations that show a swirling dark matter halo, a spiderweb of filaments, and within it, a bright pinwheel of a galaxy slowly assembling, its spiral arms painted by the birth and death of billions of stars. These simulated galaxies now match our observations with startling fidelity, producing realistic populations of satellite dwarfs and galaxies with the diverse shapes we see. So we return to that pivotal question: can a universe born in silicon tell us what the real one is made of? The answer is a qualified yes. These simulations do not prove a specific dark matter particle, but they show us which ideas remain plausible. They demonstrate that the apparent problems at small scales can potentially be solved within the standard model, not by changing dark matter, but by fully accounting for the transformative power of starlight and explosions. Each successful simulation is a guide, narrowing the vast landscape of possibility and showing us where to point our telescopes and our most sensitive detectors next. A single, unexplained flash is a curiosity. A pattern of whispers across the entire spectrum of reality is a revelation. This is the core promise of the multi-messenger era, a fundamental shift in how we explore the cosmos. Instead of listening with just one kind of ear, we are now learning to hear the universe in stereo, combining the language of light with the messages carried by ghostly neutrinos, ripples in space-time, and atomic nuclei hurtling from the depths of space. For the dark matter hunt, this integrated approach is not just an upgrade, it is a necessity. As one astrophysicist deeply involved in these collaborations notes, we are moving from looking for a needle in a haystack to understanding the haystack itself through every sense we possess. Power lies in correlation. A faint bump of gamma rays from a dwarf galaxy could be a statistical fluke or an unknown pulsar. A subtle excess of neutrinos from the same patch of sky could have other origins. But if both signals arrive together from the same dark matter-rich region and tell a consistent story about energy and distribution, the case for a common, exotic source becomes exponentially stronger. It is the difference between hearing a single, strange sound in the night and simultaneously feeling a vibration, seeing a shadow, and recording a temperature drop, all pointing to the same unseen presence in the room. Our new sensory array is unprecedented. Consider the coordinated watch on a target like the dwarf galaxy Sculptor, a pristine sphere of stars thought to be dominated by dark matter. The Fermi Gamma Ray Space Telescope scans it for any unusual high-energy photons. Deep in the Antarctic ice, the Ice Cube Neutrino Observatory monitors for neutrinos that might trace back to its direction, particles born from potential dark matter annihilations. On the ground, the Laser Interferometer Gravitational Wave Observatory, LIGO, and its partners listen for the faint chirps of merging black holes or neutron stars within such galaxies, events that could also produce flashes of light and neutrinos, helping us map the environments where dark matter resides. These instruments do not operate in isolation. When an intriguing event occurs, automated alerts flash across a global network, prompting telescopes around the world and in space to swing into action, capturing data across the electromagnetic spectrum. For a dark matter search, the strategy is more sustained, a long-term, simultaneous stare at promising targets. Imagine a hypothetical signature. A specific model of dark matter annihilation predicts it should produce both gamma rays and neutrinos in a particular ratio. Observatories collect data for years. Scientists then create a multi-messenger map, overlaying the faint gamma ray glow from Fermi with the neutrino event map from IceCube. On the graph, a small but statistically significant hotspot appears in both datasets, precisely aligned with the center of the Sculptor dwarf. The energy spectrum of the gamma rays and the estimated energies of the neutrinos even tell a matching tale. This confluence would be extraordinarily difficult to dismiss as background noise. The approach also opens doors for more exotic possibilities. Could certain dark matter candidates, like primordial black holes, reveal themselves through subtle influences on gravitational wave signals from merging stars? Could a burst of cosmic rays detected by instruments on the International Space Station correlate with a specific neutrino flare, hinting at a dark matter decay event? Each messenger provides a different piece of the puzzle. Light tells us about interactions with electromagnetism. Neutrinos tell us about nuclear processes. Gravitational waves tell us about violent motion and space-time curvature. Cosmic rays tell us about accelerated particles. By weaving these threads together, we can construct a profile of the ghost that is far richer than any single measurement could provide. This leads to a profound shift in perspective. For decades, we have designed experiments to detect one specific predicted signal. Now, we are building an observational net so wide and so interconnected that it can catch surprises, patterns we did not explicitly predict. The ultimate discovery may not look like a single dot on a screen, but like a constellation of faint, correlated dots appearing across multiple maps of the sky, a hidden picture only visible when every layer is placed together. Are we, in our search for a singular answer, actually learning to perceive a new, multidimensional language of the cosmos itself? The ghost we chase in the cosmos may be the key that unlocks the universe's deepest rulebook. For decades, the search for dark matter has been framed as a hunt for a missing piece of the cosmic puzzle, a hidden component that explains why galaxies hold together. But step back, and a far grander vision comes into focus. This is not merely about finding what is missing from our maps of the sky. It is about discovering what is missing from our most fundamental laws of nature. The identity of dark matter could be the gateway to a new physics, a reality beyond the standard model that has governed particle physics for half a century. As one leading theorist has expressed, dark matter is not an isolated anomaly. It is a profound clue, a message from the universe that our current understanding is beautifully incomplete. The standard model itself is a masterpiece, explaining the forces and particles that make up every star, planet, and person. Yet it is also glaringly incomplete. It contains no suitable candidate for dark matter. It cannot explain the overwhelming dominance of matter over antimatter in the universe. It leaves gravity, the force that shapes the cosmos, disconnected from the quantum realm. Most puzzling of all is the hierarchy problem, a question of absurdly fine tuning. Why is the Higgs boson, the particle that gives others mass, so astonishingly light compared to the dizzying energies at which fundamental forces might unify? The math suggests it should be billions of times heavier unless some hidden symmetry is protecting it. This is where dark matter enters, not as an afterthought, but as a potential cornerstone of the solution. The most elegant proposed fix is a principle called supersymmetry. This theory posits that every known particle has a heavier, shadowy twin, a superpartner. This doubling of the cosmic roster introduces a beautiful symmetry that naturally stabilizes the Higgs mass, solving the hierarchy problem with a single, sweeping idea. And here lies the breathtaking connection. In most supersymmetric models, the lightest of these new superparticles is stable, neutral, and only interacts weakly. It is, in essence, a perfect weakly interacting massive particle, a WIMP. The dark matter haunting our galaxies could be the lightest supersymmetric particle, a relic from the early universe whose existence was predicted not to explain missing mass, but to solve a deep flaw in our understanding of mass itself. In this view, dark matter is not a separate mystery. It is a direct consequence of fixing one of the most fundamental problems in physics. The hunt in deep underground labs and at particle colliders becomes a test of this grand unification. Finding a WIMP would not just fill in a blank on the cosmological inventory. It would validate a sweeping new symmetry of nature, a framework that could ultimately weave gravity into the quantum tapestry and point toward a theory of everything. Consider the metaphor of a great arch. The visible universe, all the stars and galaxies we see, represents one side of the structure. Our current standard model of particle physics is the other. They are held apart, disconnected by deep theoretical gaps. Dark matter may be the keystone that slots into the top, locking both sides together into a stable, coherent whole. Its discovery would complete the arch, revealing a single, unified architecture underlying all of reality. This potential elevates the search from a specialized astronomical pursuit to one of the central endeavors of all modern science. Could solving the dark matter mystery also resolve the hierarchy problem, illuminate the nature of the Higgs field, and guide us toward a unified description of all forces? The answer, many physicists believe, could be yes. The ghost in the machine of the cosmos might be the very signal that a deeper, more symmetric, and more complete machine exists. A galaxy is a story waiting to be read, and for over a decade, millions of people around the world have helped turn the page. The quest to map dark matter is not confined to mountain tunnels or supercomputers. It thrives on the home computers and curious minds of a global community. This is the world of citizen science, where the collective curiosity of the public becomes a powerful instrument for discovery. Projects like Galaxy Zoo and Einstein at Home have transformed the hunt into a shared human endeavor, proving that you do not need a PhD to contribute to the frontiers of cosmology. The principle is both simple and profound. Our most advanced telescopes produce more data than any team of professional scientists could ever hope to analyze alone. An image from a sky survey might contain millions of galaxies, each one a potential clue to the distribution of dark matter through gravitational lensing or unusual structure. While algorithms are good at certain tasks, the human brain remains unparalleled at pattern recognition, at spotting the strange and the beautiful that a computer might dismiss as noise. Galaxy Zoo harnessed this power by inviting volunteers to look at images of galaxies and answer simple questions. Is it smooth or featured? Does it have a spiral structure? Is there anything odd? What began as a way to classify shapes quickly revealed that the public could make genuine discoveries. A Dutch schoolteacher named Hanny van Arkel was examining an image when she noticed a strange, glowing green cloud near a galaxy, an object unlike anything in the catalogs. Her curiosity flagged it for professional astronomers, leading to the identification of a new type of astronomical object, now called Hanny's voorwerp. This was not a dark matter signal, but it demonstrated the potential of thousands of eyes scanning the sky. For dark matter specifically, this public scrutiny is invaluable. The subtle distortions of weak gravitational lensing, the telltale arcs and rings of strong lensing, these are often first identified by volunteers sifting through image after image. One volunteer, for instance, spotted a rare and exquisite example of a quadruple gravitational lens, a single distant quasar whose light was split into 4 distinct images by the gravity of an intervening galaxy cluster, a perfect demonstration of the warping power of unseen mass. The project's founder once remarked that the volunteers often see things the professionals miss, because they bring fresh eyes and relentless attention to the data. Beyond visual inspection, distributed computing projects like Einstein at Home offer another avenue. This platform allows anyone to donate idle processing power on their home computer to help sift through mountains of data from observatories like LIGO and radio telescopes. Your laptop could be analyzing the faint whispers of pulsars, rapidly spinning neutron stars whose precise timing might be perturbed by the gravitational influence of passing dark matter objects, or even by the collective hum of the action field. These projects create a global supercomputer, piecing together signals too faint for any single machine to find. The value of this collective effort is twofold. First, it processes data on a scale that would otherwise be impossible, scanning for needles in a cosmic haystack. Second, and perhaps more importantly, it democratizes the scientific process. It invites people to become active participants in the story, to feel the thrill of looking at a piece of the universe no one may have studied in detail before. When you classify a galaxy, you are not just clicking an image, you are helping to build the map upon which dark matter's shadow is traced. This leads to a reflective question about the nature of modern discovery. In an age of overwhelming data, is collective human curiosity not just a helpful tool, but an essential scientific instrument? The hunt for dark matter is a puzzle of cosmic scale, and it turns out that the most powerful resource we have to solve it might be our shared sense of wonder, woven together through the quiet contributions of millions. The search for an invisible cosmic substance might seem like the purest form of abstract science, a quest with no practical end. Yet the relentless drive to hear a ghost has forced us to build a new kind of world, one of impossible quiet and exquisite sensitivity. The technological mountains climbed in this hunt have not just peered into the cosmos, they have reshaped life on Earth. As one engineer working on a dark matter detector put it, we are constantly inventing tools to listen to nothing, and those tools are now hearing everything else. The need to shield a detector from the faintest whisper of natural radioactivity led to the creation of ultra-low background materials. Scientists scoured the planet for metals with minimal intrinsic radiation, eventually turning to lead recovered from ancient Roman shipwrecks, submerged for 2 millennia, its radioactivity long decayed away. The techniques developed to certify this purity, called low background assay, are now gold standards in environmental monitoring and nuclear safety, used to detect trace radioactive contaminants in air, water, and soil with unprecedented precision. The quest for absolute silence demanded revolutions in cryogenics, the science of extreme cold. To sense the faint heat from a potential dark matter collision, detectors must operate within a fraction of a degree above absolute zero. Maintaining such temperatures in large, complex instruments pushed the boundaries of refrigeration technology. These advances ripple outward, improving the efficiency of liquid natural gas transport, enabling more powerful magnetic resonance imaging machines for hospitals, and providing the stable, ultra-cold environments essential for developing quantum computers. Even the way we handle data has been transformed. The faint signals hunted in mountains of noise required new, sophisticated algorithms for pattern recognition and noise filtering. These computational techniques, born in physics laboratories, now enhance medical imaging scans, helping radiologists spot subtle early signs of illness with greater clarity. They improve seismic monitoring networks, and they refine the signal processing in global communication systems. Consider a specific thread, the development of ultra-pure silicon detectors. Initially crafted to sense the rare kick of a dark matter particle, their incredible sensitivity to ionization makes them perfect for other roles. They are now deployed in compact, highly accurate radiation monitors for first responders and in space telescopes mapping the sky in X-rays. The collaboration behind the XENONnT experiment, for instance, didn't just build a dark matter detector. It became a world-leading center for the science of measuring almost nothing, a skill in high demand across multiple industries. An industry partner working with the laboratory noted that the precision they achieve in filtering out background is something we simply could not develop in a corporate setting. The fundamental questions drive a different kind of innovation. So we are left with a reflective and deeply practical question. If the primary goal of finding dark matter remains, for now, just out of reach, does the journey itself justify the immense endeavor? The answer is written in the technologies that now monitor our environment, aid in medical diagnosis, and secure our infrastructure. The tangible progress, the unexpected solutions born from confronting an impossible problem, stands as a powerful testament to the hidden value of curiosity-driven research. We set out to map the shadows of the cosmos, and in doing so, we learn to see our own world in an entirely new light. The nature of reality itself shifts beneath our feet when we accept that most of what exists is not like us. For centuries, our understanding of matter was built from the ground up, from the rocks beneath our feet to the stars above our heads. We assumed the cosmos was made of the same fundamental stuff we could touch, weigh, and see. Dark matter shatters that assumption. If confirmed, it means the overwhelming majority of the universe's material content is composed of a substance that does not reflect light, does not form atoms, and does not participate in the chemistry of life. We are not the standard, we are the rare exception, a delicate afterthought in a cosmos dominated by shadow. This realization carries a philosophical weight as profound as any scientific finding. It forces a Copernican-level humility, not just about our place in space, but about our very substance. As one philosopher of science has noted, it challenges the most basic empirical definitions of what we call matter. If matter is defined by what we can interact with through forces like electromagnetism, then dark matter, by that old definition, is not matter at all. It is something else entirely, a category of existence we are only beginning to name. This pushes us to reconsider the nature of scientific knowledge itself. How do we know something is real if we cannot see it, touch it, or make it react in any laboratory in the traditional sense? The answer lies in the power of inference, the logical deduction from effect to cause. This is not a new method in science, it is its bedrock. We did not see the planet Neptune directly before predicting its existence. We saw the wobble in Uranus's orbit, an effect that demanded an unseen cause. We did not see the atom with our eyes for millennia, but we understood its reality from the patterns of chemistry and the tracks in cloud chambers. Dark matter is the latest and grandest chapter in this story of inferential discovery. Its reality is not proven by a direct image, but by the undeniable gravitational hand it has placed on the visible cosmos, from the rotation of galaxies to the bending of light across the universe. This process redefines what it means to observe. An observation is not merely a photon hitting a retina or a sensor. It is the interpretation of a pattern in nature that points unequivocally to a source. In this way, we have observed dark matter as clearly as we once observed Neptune, through the disturbances it creates in the fabric of the known. The implications ripple outward, suggesting a cosmos of layered realities. If this one vast, invisible component has remained hidden for so long, what other forms of existence, equally aloof from our senses, might be woven into the universe? It opens a door to a reality far stranger and more richly textured than our anthropocentric imaginations have allowed. This quest, therefore, is more than a physics problem. It is a fundamental exploration of the limits of human comprehension. What does it mean to know the universe when most of it operates on principles forever beyond our direct sensory experience? The hunt for dark matter is ultimately a hunt for a new relationship with reality, one built not on what we can see, but on what we can deduce, a testament to the human mind's ability to reach beyond the visible and map the contours of the invisible. The silence from our deepest laboratories is a form of data, one that whispers a startling possibility. What if, after a century of meticulous searching, the dark matter paradigm is simply wrong? This is not a fringe idea, but a necessary exercise in scientific humility, a willingness to follow the evidence wherever it leads, even if that path forces us to abandon our most cherished assumptions. As physicist Richard Feynman once cautioned, the first principle is that you must not fool yourself, and you are the easiest person to fool. The strength of science lies not in stubbornly defending a theory, but in knowing precisely when to question its very foundations. We must honestly ask, could the collective weight of null results and persistent anomalies be telling us to look for a different kind of answer entirely? To stand at this crossroads is to engage in the most profound kind of scientific triage. On one side, we have the immense explanatory power of dark matter. It beautifully accounts for the large-scale structure of the universe, the pattern of the cosmic microwave background, and the gravitational lensing we observe. It is a framework that works astonishingly well on cosmic scales. On the other side, we have the growing list of puzzles, the small-scale crises in dwarf galaxies, the profound quiet from every direct detection experiment, and the lack of any confirmed signal in the skies. The scientific community's task would be to weigh these scales carefully. At what point does patching a theory with increasingly complex additions, like baryonic feedback or exotic dark sector interactions, become less elegant than a wholesale revision of the rules? How many adjustments can we make before we admit we might be trying to fit a square peg into a round hole, no matter how beautifully we carve the edges? A post-dark matter cosmology would face a monumental challenge. It would need to explain from first principles every single phenomenon that dark matter currently addresses. It would need to derive the flat rotation curves of galaxies from a modified law of gravity. It would need to reproduce the precise acoustic peaks in the cosmic microwave background, the detailed bullet cluster observations, and the intricate web of galaxy filaments, all without invoking any unseen mass. This is a staggering burden of proof. History offers us guiding precedents. For centuries, the geocentric model of the universe, with Earth motionless at the center, was the dominant paradigm. To explain the peculiar retrograde motions of planets, astronomers added layer upon layer of complexity, introducing epicycles upon epicycles. The model could predict planetary positions with reasonable accuracy, but it was a convoluted, unnatural framework. The shift to a heliocentric model, championed by Copernicus and later refined by Kepler and Newton, was a paradigm shift that simplified our understanding by changing a foundational assumption, the center of the cosmos. Are we in a similar moment? The question we must confront is fundamental. Is the strength of a theory measured by the beauty of its predictions, or by its stubborn resilience in the face of repeated non-detection? A theory that predicts new particles we never find may be pointing us in the wrong direction. This intellectual honesty, this readiness to let go of an idea when the evidence demands it, is the bedrock of the scientific endeavor. It requires a courage equal to that of discovery, for it means admitting our map of reality was incomplete and beginning the long, hard work of drawing a new one. The universe's greatest secret is not hidden in a single place, but in the space between disciplines. For generations, astrophysicists mapped the grand architecture of galaxies, while particle physicists probed the furious collisions inside atoms. Their worlds seemed separate, one of cosmic vastness, the other of quantum minutiae. The dark matter mystery has dissolved that boundary, forging a new kind of science born from their convergence. This is a hunt that demands we read the cosmos with one hand and the subatomic rulebook with the other. An astrophysicist might describe the precise rotation curve of a dwarf galaxy, the gravitational signature of an unseen halo. A particle theorist then translates that signature into a predicted mass and interaction strength for a hypothetical particle. An experimentalist deep underground designs a detector sensitive enough to catch it, while a cosmologist checks if that particle's abundance matches the recipe written in the cosmic microwave background. As one researcher famously noted, we are no longer just talking past each other at conferences, we are building a common language. The synergy is elegant and essential. Astrophysics provides the where and the why. It tells us dark matter must exist in these quantities, distributed in these specific halos, sculpting the universe in these observable ways. Particle physics provides the what and the how. It proposes the candidate particles or fields that could fulfill that cosmic job description, and it designs the experiments to manufacture or capture them. Nuclear physicists contribute their deep understanding of how particles interact with atomic nuclei, which is crucial for interpreting the faint signals in direct detection experiments. Even engineers and data scientists become central players, creating the impossibly quiet environments and sophisticated algorithms needed to hear the signal. This breaking down of silos is a hallmark of 21st century big science. The ultimate proof will not come from a single experiment in isolation. A true discovery will be claimed only when multiple, independent lines of evidence converge into an undeniable picture. Imagine a hypothetical future announcement. First, an underground laboratory like Darwin reports a statistically robust signal, a clear pattern of nuclear recoils that cannot be explained by any known background. Simultaneously, the Cherenkov telescope array reveals an excess of gamma rays from several dwarf galaxies, with an energy spectrum that perfectly matches the predicted annihilation products of the same particle. To crown it, the Large Hadron Collider identifies missing energy events that point to the production of a new, weakly interacting particle with a mass consistent with the other two signals. Only when this triad of evidence aligns, astrophysical, direct, and collider-based, will the scientific community move to claim a discovery. The process is governed by rigorous protocols and international committees designed to prevent premature excitement and ensure global scrutiny. We have a blueprint for this in the discovery of the Higgs boson. That was not a single eureka, a moment in one lab, but a years-long, coordinated effort between the enormous ATLAS and CMS collaborations at CERN. They independently collected and analyzed data, cross-checking each other's work, until the combined evidence reached a definitive statistical threshold. The announcement was a carefully orchestrated event, a testament to the power and patience of large-scale collaboration. This model now guides the dark matter search, but on an even grander, more interdisciplinary scale. So we must ask, in an age where knowledge often fragments into ever narrower specialties, is our greatest cosmic mystery forcing us to rediscover the power of working together? The convergence is more than a strategy, it is a new way of seeing. It suggests that the answers to the biggest questions are woven into the fabric of reality at every scale, waiting for us to learn how to listen with every tool and every mind we have. History's greatest discoveries often arrived unannounced. Alexander Fleming returned from vacation to find a mold, penicillium, halting bacterial growth on a forgotten Petri dish. Arno Penzias and Robert Wilson, trying to eliminate a persistent hiss from their radio antenna, stumbled upon the echo of the Big Bang itself. These were not the results of targeted search, but of prepared minds recognizing the profound significance of a chance observation. This is the power of serendipity, the fortunate accident, and it is woven into the very fabric of scientific progress. As the chemist Louis Pasteur famously reflected, chance favors only the prepared mind. In the hunt for dark matter, this principle is not a side note, it is a vital strategy. Our most sophisticated machines, built with one specific goal in mind, might very well reveal the answer while looking at something else entirely. Consider the architecture of modern physics. A gravitational wave observatory like LIGO is designed to catch the ripples from colliding black holes and neutron stars. Its lasers measure distortions in spacetime 1,000 times smaller than an atomic nucleus. But what if, buried in that exquisite sensitivity, is a different kind of tremor? A dense clump of dark matter, like a primordial black hole or a macroscopic cue ball, passing near the Earth could theoretically create a minuscule, distinctive ping in the detectors. It would be a signal utterly unlike the classic chirp of a merger, a subtle, perhaps repeating, signature that the original analysis algorithms were not trained to find. It would take a curious researcher sifting through the data with an open mind to flag that anomaly and ask a new question. This is how serendipity operates in the age of big data. It is not merely luck but a systematic openness, Experiments now collect petabytes of information, a vast digital universe of measurements. Within that universe, there are bound to be outliers, blips, and curiosities that do not fit any known category. The critical step is having the flexibility and the funding to chase them down. When the X-ray satellite Rosat scanned the sky in the 1990s, its primary mission was to map high-energy sources. In the process, it detected an unexplained diffuse glow of X-rays, later called the X-ray background. While its origin was eventually traced to distant quasars, for a time it was a major puzzle, a classic example of an unexpected signal demanding explanation. The dark matter search is ripe for such a moment. An instrument like the Fermi Gamma Ray Space Telescope, while scanning for pulsars and blazars, could record a faint, anomalous line of photons that resists all astrophysical interpretation. A tabletop experiment studying the quantum properties of neutrons might record a tiny, periodic shift in their behavior that points to an interaction with a background field, like that of Axions. History offers a clear guide. The planet Uranus was discovered by William Herschel in 1781, while he was systematically charting stars, not searching for new worlds. The electron was identified by J.J. Thomson during experiments on cathode rays, which he thought were a form of light. In each case, the discoverer was investigating one phenomenon and stumbled upon the evidence for something far more fundamental because they were willing to follow the anomaly. For dark matter, this path is not just possible, it is statistically likely. With dozens of major experiments running worldwide, each probing a different corner of parameter space, the chance that one will record an unanticipated signal grows every year. The key is in the culture of science itself. Researchers must be encouraged to spend time on strange, low-probability events, to reanalyze old data with new hypotheses, and to share curious findings that do not fit the mold. As astronomer Vera Rubin herself noted, major leaps forward often involve discarding a cherished assumption. Are our collaborations and institutions structured to reward that kind of intellectual risk-taking, or are they optimized only for confirming predefined models? This injects a thrilling element of unpredictability into the decades-long quest. The answer may not arrive with a press conference from a flagship dark matter experiment. It might instead emerge from a graduate student's thesis as they pore over publicly released data from a particle collider or a radio telescope, finding a correlation that everyone else had filtered out as noise. It could come from a small, innovative lab testing a new quantum sensor for computing, only to find it is inexplicably sensitive to a background oscillation that matches a dark matter field. The moment of discovery, therefore, might be quiet, confused, and hotly debated at first. It will require the collective courage of the scientific community to pivot and investigate the unexpected, to entertain the possibility that the ghost revealed itself not in the darkness we prepared for it, but in a sliver of light we had ignored. Are we, in our meticulous planning and targeted searches, also preparing our minds for the fortunate accident? Our journey began with a single, flat line on a graph, a stubborn fact that refused to fit the story we told ourselves about the universe. From Vera Rubin's meticulous observations at her telescope to the silent cathedrals built a mile beneath the Earth, we have chased a ghost across every scale of reality. We have mapped its shadow with gravitational lenses, listened for its hum in resonant cavities, and tried to conjure it in the fiery hearts of particle colliders. We have built a global network of curiosity, where astrophysicists, particle theorists, and engineers speak a common language, all focused on one profound absence. The fact that dark matter continues to evade every trap we set is not a story of scientific failure. It is the opposite. It is a testament to the profound strangeness of the cosmos and the incredible rigor of our methods. Each silent detector, each null result, is a data point that carves away a piece of the possible, forcing us to think more creatively and to look more deeply than ever before. This epic hunt is driven by the purest human impulses, curiosity about our place in the grand scheme, and a collaborative drive to peel back the layers of reality. The astronomer Carl Sagan once reflected that the pursuit of knowledge is preferable to its illusion, and in the tireless search for dark matter, we see that nobility in action. We are not just looking for a missing ingredient, we are trying to complete a new picture of existence, one where most of the universe is made of something fundamentally unlike ourselves. This story is far from over. New telescopes will scan with sharper eyes, and next-generation detectors will listen in deeper silence. The answer is out there, waiting in the data or in the next fortunate accident. I encourage you to stay curious, to follow the announcements from labs and observatories as this century's greatest detective story unfolds. The universe is still full of secrets, and that is what makes it so wondrous. If you want to join more explorations into the mysteries of space, consider subscribing. And I would love to hear your thoughts. Which dark matter candidate seems most compelling to you? Or what cosmic question keeps you wondering? Share it in the comments below. From the invisible threads of the cosmic web to the quiet hum of a detector waiting for a whisper, the search continues, a beautiful reminder that the greatest adventures begin with admitting what we do not know.